There are moments in astronomy when a familiar process reveals a single new detail, and that detail forces us to recheck the mathematics and rethink the assumptions beneath it. For more than a century, we have catalogued comets and asteroids as they wander through the solar system, each shaped by gravity, sunlight, rotation, and nothing more exotic. Every so often, however, an object shows up that refuses those expectations. 3I Atlas is one of those objects. From the instant it first appeared in our survey images, we knew it was different. Its incoming vector, its unusually high heliocentric velocity, and its orbital elements marked it as an interstellar traveler, the third confirmed visitor from another star after Oumuamua and 2I Borisov. Interstellar objects are scientific messengers. They bring chemistry and materials forged around other suns. They give us windows into processes we cannot reproduce in our labs. But what has unfolded since discovery goes beyond the simple thrill of an interstellar sample. 3I Atlas is not merely passing through, it is showing a subtle but measurable non-gravitational acceleration that is steering it toward a remarkably precise location in our system, the boundary of Jupiter's sphere of influence, the Hill radius. Current models place the closest approach at 0.357 AU. At first glance, that looks like a technical datum, but viewed through dynamics, it is astonishingly significant. That distance puts 3I Atlas almost exactly on the edge of Jupiter's Hill sphere, the region where Jupiter's gravity prevails over the Sun's. For a random object arriving from interstellar space, the odds of threading that needle within fractions of an astronomical unit are vanishingly small. Yet multiple independent orbit solutions, even when they incorporate measurement uncertainties and non-gravitational terms, converge on the same result. This object is threading a narrow gravitational keyhole. To understand why that matters, we must revisit what a Hill sphere is. Every planet has a zone where its pull overrides the sun's. It defines the region where satellites can be retained and where passing bodies can be captured or dramatically deflected. For Earth, the radius is modest. For Jupiter, it is vast. Roughly 0.355 AU, 3I Atlas's projected path, at 0.357 AU, lies only about 0.002 AU outside that boundary, a separation on the order of 300,000 kilometers, roughly the Earth-Moon distance. That closeness is not trivial. It turns a routine flyby into a finely tuned dynamical test. So how probable is such a pass by pure chance? Basic geometry and isotropic arrival assumptions give a blunt answer, extremely unlikely on the order of 1 in a few 100,000, but probability alone is not the whole story. When researchers fold-measured non-gravitational accelerations into trajectory simulations, the small, persistent thrusts inferred from jet activity, the intersection with Jupiter's Hill sphere remains robust. In other words, the extra forces acting on 3I Atlas are not random noise, they bias the path consistently toward that narrow boundary. Non-gravitational accelerations are not unheard of. Comets commonly exhibit them due to asymmetric outgassing, but for solar-borne comets those forces are often stochastic, variable in direction and magnitude, as jets open and close with rotation. For an interstellar object with no prior dynamical relationship to our system, the persistent directionality we observe is unusual. The acceleration we now measure exceeds conventional detection thresholds, in some analyses reaching significance well above standard noise floors, and it aligns with the inferred direction of mass loss. Let's walk through the physical picture. Early observations in July through September showed only minimal non-gravitational terms, allowing analysts to place a lower bound on the object's mass, on the order of 33 billion tons. That is a substantial nucleus. But near perihelion in late October, the object's behavior changed. Acceleration signals rose to high statistical significance. The effect is consistent with directional mass ejection, jets emitting material preferentially in a way that produces a net thrust. If we assume simple sublimation-driven jets, the required mass loss to account for the measured acceleration is enormous, billions of tons over months, which raises immediate physical questions about volatile reservoirs and mechanisms at the distances involved. Spectroscopy offers partial clues. Multiple teams report bright comet and signatures consistent with volatile carbon-bearing species, carbon monoxide and other low-temperature volatiles, which can sublimate far from the sun. The precise molecular inventory remains under review. Mainstream facilities are still converging on consensus identifications. What is clear is that the coma is active and substantial, and the ejected material can exert measurable forces that, when integrated over hundreds of millions of kilometers, produce cumulative steering effects. when those non-gravitational terms are fed into trajectory integrators, the same tools used by JPL Horizons and orbital mechanics groups worldwide, a pattern emerges. Thousands of simulated clones spanning the uncertainty envelope repeatedly thread very close to Jupiter's Hill sphere. In many simulations, the object would miss the margin if the non-gravitational component were absent. With the component included, convergence toward the L.357 AU corridor is common. That empirical robustness is what we call non-gravitational steering, forces other than gravity shaping the long-range path. To be clear, steering does not imply anything supernatural. It means simply that processes like anisotropic outgassing, jet geometry, rotational phase, and compositional heterogeneity are contributing directional thrust. The exact mechanisms, whether steady, episodic, or tied to localized vents, remain to be determined, but the forthcoming encounter gives us a controlled opportunity to test these ideas. Why is the March 2026 window so vital? Because it is the date when the cumulative effect of those subtle accelerations will be most cleanly measurable in Jupiter's gravitational context. Spacecraft and ground assets can observe the interaction from multiple vantage points. If mission planning permits, NASA's Juno could be repurposed to observe the approach between March 9 and March 22, 2026, a unique chance to capture coma morphology, jet geometry, rotational signatures, and surface reflectivity at closer range than Earthbound telescopes allow. Large observatories in Chile, Spain, and Hawaii will run coordinated spectroscopy campaigns to pin down volatile species, search for Doppler shifts linked to jets, and map rotational harmonics. Refined motion solutions from JPL and others will let us reverse engineer the mass loss geometry, test models of thrust production, and place constraints on internal structure. The encounter is an unprecedented natural experiment, an interstellar body interacting with our system's largest planet under measurable non-gravitational forces. So what do we know now without hyperbole? First, 3I Atlas is confirmed interstellar by its trajectory. Second, it is losing mass rapidly and exhibiting measurable non-gravitational acceleration. Third, the acceleration is sufficient to alter its path and lead to a close approach at 0.357 AU from Jupiter in March 2026. Fourth, the computed probability of such an intersection by random chance is exceptionally low. Fifth, Earth and space-based assets can observe and refine our knowledge before, during, and after the passage. What we do not yet know in detail are the exact volatile inventory, the three-dimensional distribution of mass loss, the precise rotation state, and whether the mass loss is steady or episodic. We cannot yet map the nucleus in 3 dimensions, nor can we fully resolve the jet geometry. Those are the unknowns that March 2026 can help answer. This event is not the end of a mystery, it is the opening chapter of a new kind of experiment. For the first time, we will predict in advance the close approach of an interstellar object to a major planet and coordinate a global observational effort around that forecast. Whether the ultimate explanation lies within known cometary physics, exotic chemistry, or unexpected internal structure, each outcome will deepen our knowledge of interstellar material and dynamics. 3I Atlas forces us to confront the interplay between the familiar, the gravities and orbits we have long modeled, and the foreign materials and behaviors formed under other suns. The 0.357 AU passage is the sharpest dynamical feature yet recorded for an interstellar object. It threads together gravity, outgassing, rotation, and radiation into a test we can observe, measure, and learn from. Science advances when nature hands us precise experiments at times we can study. 3I Atlas has given us such an experiment. Over the next 16 months, we will learn how much the cosmos can teach when we listen carefully, model rigorously, and let the evidence lead the way.